Okay. So to estimate the model, again, review. And there are 3 parameters here. We should give priors to them for this model. And then if you have limited prior information, let's just do a weak informative prior. And as we discussed earlier, I think when Maggie was asking the question, how can we choose prior? I think for now, let's just think that, well, the prior is probably the weaker, the better, because we want to use the data to let the data to drive the inference, because then you will have a model being estimated, or I should say the estimated parameters will be very close to what the data is telling us. And then that can help us to improve the utility of the synthetic data that you're going to generate. Okay. So we're going to assume independence of the 3 parameters. And then for each of them, I already talked about it. Beta 0, beta 1, typically you can use normal priors for them, especially if they can be centered at 0 and with a large spread. So I'm using mu0, mu1 for the means, and S0, S1 for the standard deviation. You can use mu0, mu1 to be 0, and S0, S1 to be 100. You can change, probably wouldn't change that much if you change the value of S0, S1. Here, we're just trying to give a really weak informative prior. For 1 over sigma squared, which is the precision, you can give gamma 1, 1. Okay, this is sort of what we talked about before in 347. So hopefully it's a review, but refreshing your memory of what you can do. Okay. All right, so MCMC simulation, we just want to use JAX for now. It's not something very complicated, and also a good thing to refresh your memory about. So we're going to use JAX. It's just another GIF sampler to estimate our chosen Bayesian simple linear regression model. And I highlight this one here just to make sure that, well, if you remember, for simple linear regression, typically, like we give priors, we run JAX, we get some output, and then we do some interpretation or like summarization of the parameters. Like we talk about, well, the mean or the median of the beta 0 and beta 1, right? And then we talk about their interpretation. Say beta 0, we know is the intercept. So we can talk about, well, if it's 95% credible interval is from what to what, then we can talk about, well, on average, if you have a CU with log expenditure to be 0, right, then what the log income will be, because that's what intercept is about, right? And then beta 1 is the slope. So we know that it's 1 unit change in the predictor. On average, how much change you will see in the response. So that's typically what we do when we do simple linear regression, when we try to make inference. And you can also do predictions or any kind of things. But for synthesis purpose, that's what we focus in this course right now, is that we not only, so the goal really is that we want to get posterior draws of beta 0, beta 1, and don't forget, we also have sigma, they're all parameters. So we want to get posterior draws for all of this from our JAX output, because we have to use them later to do predictions to synthesize the sensitive variables. So I highlight over here that you will, well, remember in JAX you can define how many samples you want, how many thinning, all that. So you're gonna pre-specify how many posterior parameter draws from the JAX output that you're going to get from your JAX code, and then make sure that like the process doesn't end there. We have to do prediction in order to get synthetic data. Okay, so keep that in mind. But you will see the sample script that I will provide today. Will just walk you through that. And make sure that so run JAX, that package is for doing JAX, okay, in R. And also make sure that, I'm sure, like if you didn't delete anything from your laptop, you probably will still have JAX, the software itself installed. But if you accidentally don't have it anymore, I will send the link where you can download for your computer. And because run JAX is just a R package that you can run JAX software from R, but you also need to have JAX installed first, just like the relationship between R and RStudio. Like R is the programming, I mean, it's the software that is doing, but RStudio is a friendly interface, so you have to have both of them before you can run anything. And the other package that we're going to use, you probably don't remember this that much, is the Coda package. So we're using this mostly because we were trying to extract the posterior draws from your JAX code, JAX output. And this, this package is just handy when you're trying to get those draws into data frame and then do things about them later. Okay. I think in 347, a lot of times we sort of like stopped at round JAX, because as soon as you can run JAX, then, oh, that's fine, round JAX. As soon as you can run JAX, you will, well, you will get those MCMC outputs. Sorry, it's not that funny, I guess. No, it just occurred to me how they make the name, I guess. Never mind, it's okay. So when you have that, then remember like those MCMC diagnostics, it's actually just in that package itself. You can do the plot, and then you can see like all of the trace plots, what else, autocorrelation plots, all that automatically. So in the past, I think in 347, only if we're doing predictive, posterior predictive, we were using this Coda package, okay? But now we need them because we are trying to generate synthetic data given the posterior predictive distribution. Okay, so these are the two, and that we will need. So, all right, so we won't walk through like the detail of how to write the script and all that, but I hope you will take the time to review, especially if you, for next time, if you were to do a different model and then try to use JAX to estimate the model and then generate synthetic data, you will have to like, I guess, make sure that you understand all of this. But this is the model string that we typically use for JAX when we're trying to write the model, which has the sampling chunk, right? That's the sampling model, which is a normal. Beta 0 plus beta 1 times the predictor, predictor, and then the sigma, and then also the chunk for the prior. Okay. So that's the first part. Second part is define the data and the prior parameters. I will leave that to you to try again later. So make sure that you pass the correct vector into your y or x and all the other things. And the data part, this list is storing all of the, not only the y, x, and n, but also the hyperparameters that you use for those priors. So this is following this two is the normal, right? It's the normal 0 and 100 that we give beta 0 and beta 1. And don't forget that JAX takes precision instead of standard deviation. That's why you have to do all of this. And this A and B is for the gamma prior or your precision parameter. Okay, gamma 1, 1. And this part, if you remember, this is trying to make your results reproducible. So JAX would take not the set seed like in R, but you have to set seed in this way. So that's why we put it over there. So we'll have reproducible results. Part 3 of this, is generate samples from the posterior distribution. Is now where you use this round.jax function. And then, typically I think you do one chain is good, right? And then you can decide what parameters you want to return. For us, we want everything because we need parameter draws for every parameter to do prediction. Okay. Sometimes, if you're only curious about the inference, maybe like a lot of times people don't care about the intercept at all. So if you only care about like the slope and the sigma, and sometimes maybe just the slope, then you just need to monitor one. But for our purpose, because we need to do predictions afterwards, you have to save parameters, save draws for all of the parameters. You cannot like miss anyone. So in this case, it's all of them. And here, so adapt, burn in, and then sample. So I'm using 5,000 for now. We can see whether we need that many later, but we need this many usually for MCMC diagnostics, right? Like you want to see the chain has converged and all that. So we do that. I set the thing to be 50 just because when I run with 1 in the first place, it's highly correlated, so I just set it to be 50. So that's why I write it over here. Okay, but again, this is a try and error process. You all know that. You will have to determine how many thinning you're going to do given the model that you have run. Okay. So part 4, MCMC diagnostics, you should do that for all of the parameters. Here, it's just for beta 0. Okay. And you see trace plot, the 2 plots that we focus is the trace plot here, and then the autocorrelation plot. You'll see that autocorrelation is still relatively high, so you can do further thinning if you want. Okay. Yeah, but for now, I mean, for demonstration purpose, I did thin to be 50. And we know that the larger the value is thin, the longer the chain has to run, so you have to wait for a little bit longer to get the results. And the last part here is saving the parameter draws. Okay, so this is the part where you use the CODA package. So we typically use this as MCMC, and then posterior was the output, right? It was the like posterior is the output of the round.jax function. So you turn that into a MCMC object. That's what they mean for as.mcmc, and I'm saving it in post. And it is from here that I'm gonna get the draws for beta 0, beta 1, and sigma. Okay. So remember the monitor just now. Let me go back here. The monitor is beta 0, beta 1, and sigma. So soon you will see that that's like each column of the post that we just saved corresponds to each of the parameters here. Okay, so it will be easy for us to extract them later when we're doing the synthesis process. Okay. All right, so again, I highlight here in red just to get us into thinking that we need to make sure that we are getting the posterior draws, because we use them later for posterior predictive distribution generation. So just to explore this post a little bit, if you round those lines on your own machine, you will see that in the end, the post contains 5,000 rows, because that's how large my sample is. Remember, each row gonna be a sample. In a sense, that it's one MCMC iteration. I set sample, so this is because I set sample earlier to be 5,000. Okay, I did think of 50, but it just ran that long and then saved every 50 draws. It's gonna have 3 columns because each column corresponds to your parameters, because I monitor beta 0, beta 1, and sigma. Okay, so that's why. And then each row corresponds to one of the 5,000 MCMC iterations. Okay, so this post is what we're going to use soon to generate synthetic data set if I'm going to use this model overall to do this. All right, so we use this draws saved in post to generate synthetic values for log income. And